So here's the final section of Unit 6, which has to do with linear systems, whether it's equations or inequalities. So today we're going to put two inequalities together, basically. So we're going to solve linear systems of inequalities by graphing. So we're just taking what we did last time and kind of putting two on top of each other. I'm going to recommend that you have coordinate graph paper ready to do a few with me. And the other thing you can use are colored pencils because you're basically going to be doing shading twice. So having two different colors will help you kind of know where the intersection is. The other thing you can do is if you don't have colored pencils is kind of use like horizontal lines for the shading, going for one and vertical for the other, something like that, just so you can distinguish what's going on. So today we're going to start with a little bit of vocabulary. And a system of linear qualities is just two or more linear inequalities basically graphed together. And the solution of a system of linear inequalities is going to be the set of all the points that makes both inequalities in the system true. So the graph of a system of inequalities will show all of its solutions. So basically what we're going to do here are our marching orders. We're going to graph each inequality on the same coordinate plane. So we want to have our inequalities in a easy way to graph, in an easy form to graph, so slope intercept or standard form. So make sure you do that first. Once you do, you're going to graph both on top of each other, and the solution of the system will be the areas of overlap. If there are no areas overlap, then there would be no solution to the system. So basically what we're going to do is what we did in the last video is we're going to graph both of these inequalities, but we're going to do the first one. So the y is greater than 4x plus 3. We're going to do its shading. And that's, again, if you want to use one color or if you want to do like just make horizontal lines for the top one. And then you're going to graph the second inequality on top of it. And this time, again, a different color, or you could use vertical lines to kind of see where is the intersection area of those two inequalities. And then we're going to ask the question, is the point -2, 6 a solution to the system? So the video is going to stop so that you can do both of these, and then I will come back and make sure that we are clear. Okay, so let's start. We're going to graph. This one, I would start with my y-intercept of 3, and I would rise 4 and over 1, and my line would be dotted. I would then test a point on either side to see if it makes the top inequality true, and I would shade accordingly. On the bottom one, I could, because it's in standard form, I could possibly use the intercepts, but just be careful because I'm going to end up with a fraction here. That might make you uncomfortable. But basically, here is the first one. So there's the 3 up 4 over 1 dotted. If I test that 0, 0, 0 is greater than 3 does not work, so I have to shade the other side. So here underneath the box, I am actually switching that red equation. Sorry, my computer mouse is doing kind of weird stuff today. It's being kind of a little persnippety. But anyway, that bottom one, I added the 2x and then divided by -1, which would flip the inequality so that I could graph it in slope-intercept form. So as I go forward to see that, there would be my -1 and down 2 over 1. Now, you could have left it in standard form, but you would have seen that the x-intercept was -1/2. It's just, it's a little tricky to graph. So once I've graphed that line and tested a point, I should have shaded this side. Now the question is, where do these two inequalities have a same region shaded? And you're going to see it's kind of like this top V. So it was shaded blue for the top inequality, and it was shaded pink for the bottom inequality. So all the points in this V would make both true, and that would be our solution area. So basically the idea that all points in the area of overlap are solutions. So now to answer the question, -2, 6, since it is in that overlap um, area, it would be a solution to the system if we look at the graph. Now, the other way you could have checked to see if it was a solution is to put the -2 in for x and the 6 in for y and checked both inequalities. You'd have to do it in the blue and the red. That would be called checking it algebraically. Checking it geometrically, graphing would be to look at the graph like we did at first. Either way, the answer should be yes. All right, so now we're going to move on to another one. You're going to graph the top inequality, do your shading, graph your bottom inequality, do your shading, and then answer the point, is the point 42 a solution to the system? The video will stop here with a note for you to do that, and we'll come back and check it. Okay, so there is, if you'll notice, I did the bottom one first because it's special case. It's a horizontal line through the y-intercept of 3. Every line y equals 3 is a horizontal line, and it's dotted because this guy doesn't have the equals component, and it's everything bigger. So if you were to put 0, 0, in this case, 0, is it greater than 3? No, so you do not shade down here. Now I'm going to put my y-intercept of a -2, and I'm going to go up 5 over 2, up 5 over 2, put in my solid line, do my shading, and this would be the top one. I just did them out of order. I always like to go easy first, and to me, the y greater than 3 was easier. So now basically, if we look, the double shading should be up here. Now to get the pink shading, I don't know if I would have used 0, 0. It's kind of a little bit close to the line. Maybe 2, 1 would have been a better choice on the top one. And if we put 2 in for x and put 1 in for y, you're going to see it makes that inequality true, and that's why I shaded over here. Any point up here in this double shaded region makes the system a solution to the system. So is 4, 2 a solution? And if you see, I plot that point, and we can see that it is a solution to that pink inequality. It is not a solution to the green, so it is not a solution to the system. And again, you could have done it algebraically by doing a check basically in both inequalities. Okay, let's do one more here before we say where do we use this in the real world. So I've got 2 inequalities there. You might have to work with the top one a little before you go ahead and graph it. Again, the video will pause. You are going to graph the top inequality, the bottom, and then answer the question, is -3, -5 a solution? Okay, so starting out first, you're going to notice that I divided both sides of the blue one by 4, and so I got this inequality. If you solve the bottom one for y, you would get this inequality. And the reason I did that is I want you to see that they have the same slope, but different y-intercepts. So that should already be telling you that these guys are what we would call a special case. Same slope, different y-intercepts. Did you get parallel lines to start? So basically, here is the top one. It does not seem to have a y-intercept, which means it's 0. And then we go up 3 over 2. It's a solid line. I can't use 0, 0 as my test point. You could come out and use 3, 1, however. And if you put 3, 1 in, it doesn't work. So you would shade up here in the blue. The bottom line has a y-intercept of -3, up 3 over 2, also solid. I could put 0, 0 in that one. Is 0 less than or equal to -3 is a big no, so I shaded on the other side away from 0, 0. So if you notice here, there is no overlap, so this would be a no solution. So is -3, -5, the answer is no, because there aren't any solutions to this system. Whoops, let me just fix that again. Now, let me just, before we move on from this one, mention that if we were to switch the inequalities around, so the top one being less than or equal to, and the bottom one starting out as greater than or equal to, then what would have been the overlap? Their shading would have flipped, and there would have been a solution in between the train tracks that would have overlapped. So I'm telling you that because every time they're parallel, it doesn't mean there's no solution. You also could have left the blue one the way it is and just flipped the red one the other way around, and then the double shading would have been up above the blue one here. So don't think that just because they're parallel, there's no solution. It's because of the way the inequalities are basically pointing that made this one not have a double shading area. Okay, so I forgot. We're going to do one more before we move on. So I wanted you to see a system that involves more than two. System does not mean two, it means more than one. So here what we're going to do is we're going to graph these three. Notice we have two special cases. You're going to describe the shape of the solution area. We're going to find the vertices, which mean the corner points of that shape. A shape, I mean, like, is it a rectangle? Is it a pentagon? Is it a triangle? What is it? And then that remaining shape, you're going to find the area of. So we're going to start right now by graphing these three simultaneously on the same graph. The video will stop to allow you to do that, and then we can look at these questions. Okay, so first things first. This is sort of the way the picture should have looked. So there is your y-intercept of 1, up 1 over 2, up 1 over 2, solid line. And if you tried 0, 0, it would not work. So you would have shaded all up in here. Okay, I'm just showing you the multiple shaded region here. Otherwise, it does look a little bit like you're in a blender. Y is less than or equal to 2, horizontal line going through the y-intercept of 2, everything below. So again, sort of this region. X greater than negative 4 is a vertical line, dotted because it doesn't have the equals component, and it's everything bigger than negative 4. So what you end up with is this region right here. So describe the shape. It's a triangle. Find the vertices, and you'll see I marked those. And then you had to find the area of the region. So I'm pulling back a little bit in those brains. Do you remember how to find the area of a triangle? In this case, what kind of triangle is it? It's a right triangle, and your base and height are the two sides I am tracing. This other side over here is called the hypotenuse, and these are called the legs of the right triangle. To find the area of that triangle, you might remember that you take half the base times the height. Half the base times the height. Well, how do I get the base and the height? Count, people. 1, 2, 3. There are 3 blocks here. 1, 2, 3, 4, 5, 6. So the length of this red piece of the triangle, this red leg, would be 6 units, and it would be 3 here. 3 times 6, take half, and that's your area in square units. So it is a triangle. Here are the vertices, and it would be 9 square units. It is 1/2 the base, which is 3, times the height, which is 6. 1/2 times 3 times 6 is 1/2 times 18, which is 9. Okay, last problem. Let's talk about where do we use this. So a seafood restaurant owner ordered perch and salmon, and he wants to make sure that he has at least 50 pounds of fish. He cannot spend more than $180. You're going to write and solve a system of inequalities to show the possible combinations of perch and salmon he can buy. So this is back to a system. We had a whole worksheet on equations. Can you come up with 2, this time, inequalities? And don't forget, we need to define our variables. I'm going to start by defining the variables just so we'll all have the same sort of variables in our inequalities. So I'm going to let P be the pounds of perch. There's a shocker. And I'm going to let S be the pounds of salmon. So now, can you write 2 inequalities using the P and the S and the numbers up here in the problem? And let's see if we can solve this real world inequality problem. Okay, so there's going to be 2 inequalities. One is going to be sort of a total fish inequality, and one is going to be a total money inequality. To get the money, I hope you noticed over here that we've got some prices. So I'm going to start with, I believe, the total, which I did. So the total pounds, I have to have greater than or equal to 50. At least means 50 or more. So I'm going to P plus S is going to be greater than or equal to 50. This was like our total equation when we did sort of that packet of problems. Now I'm going to head over to money. So the perch is going to get attached to the $4. The salmon is going to get attached to the $3. And I cannot go over the $180. So now I need to be less than or equal to. So add up my perch money with my salmon money, and it's got to be smaller or equal to 180. And now I have my two inequalities. So we're going to do a graph. Notice I'm no longer using the coordinate graph paper. It doesn't make sense because I won't be using quadrants 2, 3, and 4. There's no negatives in here. Let me just get back up here what we had. So if I look at that first inequality, it's in standard form. So both my intercepts have to be 50. So when I go to put my numbers on here, I've got to get up to at least 50. Notice my title. I just chose to put my salmon on the x-axis and my perch up here. You could switch them. So set up your graph paper right now so it looks like this. And let's get our other equation here again in standard form. Take 180 divided by 4 and take 180 divided by 3, right? And those are going to be your intercepts. So if I let P be 0, 180 divided by 3, my S-intercept, my salmon intercept will be 60. And if I let the S be 0, 180 divided by 4 gives me 45 for my perch. So now we would need to put in our numbers on our X and Y axis, in this case, our S and our P. And so that it fits, we put in our intercepts, do our graph, and then we want to find some solutions that work. The video is going to pause so you can finish this graph off. So I chose to go by tens on my pounds of salmon. I chose to go by fives on my pounds of perch. Now I'm ready to put in my intercepts. Graph my lines, they're both solid. And you're going to notice when you graphed your inequalities, the double shaded region is a slim little triangle here, okay? Now I need to find points in here that would be an example of a solution. So just to show you what I mean, let's get a different color here than the reds and the blues. So there would be a sample. All of these, you could have parts of pounds, okay? But that would be one, and that would be one, and that would be one, and so forth. So let me just give you some that I have here already written out. So if we had 50 pounds of salmon and 5 pounds of perch, that would give you at least the 50 pounds, and it would not cost more than $180. So there's the example of a solution. I give how many pounds, and I explain why it's a solution, because it's at least the 50 pounds, and it does not cost more than $180. There are some others as well. You could buy all salmon and no perch and vice versa, and you'd be looking, down here, if you bought all of the salmon in here and no perch, that would be an example of a solution. So today we've been talking about systems of inequalities. And I just want you to understand that you're basically doing what the last video did, except you're doing it twice. And a little bit creative shading to show where it is double shaded. And that double shaded region, if there is one, is where all of your solutions will lie. So today, let's do some practice on systems of inequalities. And we have just finished Unit 6. I hope you have a great day, and I'll see you soon.